All right, so looking at this question number 35 from the 12.1 sequences section. All right, so what we want to do here is we want to identify the nth term of this particular sequence. In this one we can see it's going 1, 2, 3, 4, 5, 6. All right, so if it weren't for the change in signs, we would just say the nth term, right, a sub n is just going to be equal to just n, right? But unfortunately, we are changing signs. So what we're going to do so that we have that alternating sign is we're going to do -1. And if we can't just do it to the n power, because right here n is 1. And right, if we raise this to the first power, we get -1. We want this first term to be positive. So if we just go ahead and add 1 to that, right, and then multiply it by n, right, that will be the formula for the nth term of this sequence. So -1 to the n plus 1 times n will give us that alternating sign going from positive to negative right there. All right. So I'm briefly going to touch on how to use your calculator, right? How to use your calculator to help you calculate sums of sequences in series and things of that nature. Right, first thing we can do is with this particular sequence right here, we can go ahead and we can have the calculator go ahead and calculate as many successive terms of this sequence as we need to. So we don't have to do it by hand, and we can also have it sort of make a scatter plot, or a dot plot of all of the different values on the graph as well. So what we're going to do, the first thing we're going to do, after we've turned our calculator on, we're going to go to mode, right? And in mode, we're going to turn it from function mode to sequence mode, right? So you got to turn it from function to sequence. That's the first thing. Then, if you go to y equals, right, you can enter u sub n, that's just your new f, right, is going to be equal to n minus 1 over n. The rest of the settings you don't really need to do anything with, right? And so you have u sub n, and then if you go down, you have v sub n, it's just another sequence you can end, and w sub n. Primarily, we want to keep our minimum n at 0, but you can make your n min whatever you want. That's just the first value that they're going to do with it. But this is pretty much all you have to do if you just enter your sequence, and then you can go ahead and hit table. Right, if you then go ahead and hit table, it will show you a list of all of the that would be second graph. So you're going to hit second graph, right, which will bring you to your table. And that should give you all of the different terms of that sequence up as high as you need to. You can just continue to scroll down, and that gives you all the terms. Right? After you've entered u sub n is equal to n minus 1 over n, you can go ahead and just hit graph, right? And it will show you a graph of the sequence. And if you might want to go to your window and scale it correctly, but if you scale it correctly, it'll pop up like the following. It'll look like right, it'll give you a nice little plot of your sequence to show how quickly the terms in your sequence are increasing in size. Right. So that's how you can use your calculator to get as many terms of a sequence as you might need. So that's the one thing we're going to be doing with sequences and series is just, using the table to figure out, whichever term of the sequence that we would like without having to do it out by hand. And we can also use the graph to get a sense of what that looks like graphically. Another important thing that we can do, right? We have a sub n is equal to, once again, go with the same sequence here, n minus 1 over n. And let's say I want to find the sum of this sequence, the series, from n equals 1 to, let's say, 10. So I want to find the sum of the first 10 terms, right, of this sequence, which if I can just say a sub n, or I could also say n minus 1 over n here. Right. So our calculator can actually, we should, if we can, we should be able to, some of these we can do out by hand if there's certain, we have formulas for the partial sums of some of the different sequences that we've seen. This is not one of those ones, so you would have a hard time figuring out this by hand without just adding them all up. So instead of doing that, we can use the functions in our calculator. So if we go to seconds, stat, right, and scroll over to OPS. In the OPS menu, you're going to have one called sequence, and in the math menu of that one, you're going to have one called sum. These two functions can be used in concert to help you find the sum of a sequence, right? So, for instance, with this one right here, if I wanted to go ahead and find the sum of this sequence, I'm going to go sum, right, and then inside you'll put sequence, and then the arguments for the sequence is you're going to start off by putting your sequence formula, n minus 1 over n, right, and then you're going to put whatever the independent variable is, which in this case is n, which you're just going to hit x, your variable button, which is the same variable button you've used for x and everything else before. And then you're going to put the first term, you want to start at 1 and go to 10, right? And you have to put your increment as well, which means, you don't want to go 2 at a time. You want to add up the first one, then the second one, the third one. You don't want to add up like the first one, then the third one, then the fifth one, right? So you got to put 1 for your what's called your increment, and then make sure you close both of your parentheses. And if you do that, and you should get an answer of 0.875, right? That just went ahead there and summed all of those terms up for you, so 0.875. So this is how you can use your calculator to find the sum of a sequence. And so on the ones where you're actually doing you're actually finding the sum of the sequence out by hand without using a calculator, you can always check your answer against the calculator's solution, which, assuming you punched it in correctly, should be exact, right? So that's how to use your calculator to find the sum of a sequence. Talking about arithmetic sequences is annuities and amortizations, which are just financial applications of sequences and series. So annuities, and we'll just start off with an annuity. An annuity, right, is a type of investment. It's a type of investment, right, where you earn compound interest on however much you have invested, and you deposit more money into it. In addition to getting the compound interest, you could deposit more money into the annuity at regular intervals. Right, so like every month you put in a certain amount to sort of grow the investment. So it's sort of a more complex version of compound interest. We already talked about compound interest back in the exponential and logarithmic functions section. And this is sort of a more, like I said, a more advanced concept, right? And so the annuity formula works like this. We start off with, so the amount of the annuity at the beginning, right? The amount that the annuity that we start, we're just going to call M. This is our initial investment. So this is the initial amount of money that we put in to the annuity. And what happens, okay, so you earn a certain amount of interest. Let's say that you earn like 5% interest, right? And so the amount that, whoops, I'm going to do this in red. The amount that the annuity is going to be worth after a certain number of times that you've gone through here. So let's say so N is just the number of times the interest is compounded. So let's say you compound 4 times per year, right? Then A sub 4 would be, okay, after 4 months, how much money do I have in my account? If N is years, then you'd say A sub 4 would be then the amount of money I have in my account after a certain number of years. And so we need to use an exponential function, essentially, or not necessarily an exponential function in this case, but the same idea where my interest rate is little r here, and I divide that by the number of times I compound it per year, because I don't get, just like with before, if I have 5% interest annually, I don't get 5, but it compounds 4 times a year, I don't get 5% 4 times a year, I get 1/4 of 5% 4 times per year. So 1 plus r over n, right, is going to be 1.0 something, and that's going to, if you multiply that by the amount that you had before, right, that's the new amount that you have after compounding that interest, right? So you take the amount that you had in the previous, after the previous compounding period, and you multiply that by your interest rate, essentially 1 plus the interest rate over n, which is just going to increase it by that percentage, right? And that will give you the new amount that you have. But the thing is, if in this type of annuity, right, you also deposit a certain amount of money each time it compounds. So you get interest, you get compound interest from this part right here for the amount that you already had invested, and then you go in and you add a little bit more in. P is just this periodic deposit is what we call it. So you have your periodic deposit. R is your interest rate. Right. N times compounded per year. A sub n minus 1 is just the amount you had in your annuity before you compounded the interest and put the new deposit in, and n is the number of the deposit. Number of deposit or compounding period, whichever you want to think of it, because you deposit every time it compounds. So the number of deposits you've made is the same number of times that the interest is compounded. Okay, so that's a little bit confusing, and n is always, by the way, greater than or equal to 1 in this case. We start at 1 and then we go from there for this particular formula right here. Okay, so that's a little bit confusing, so let's go ahead and look at an example to try and make this a little bit more concrete. All right, so let's say you're saving for a spring break trip to Cancun. Awesome, right? The first thing we want to do here, so let's say the trip itself costs $450 and you have to pay it by March 2nd. To have the money, a student on September 1st deposits $100 in a savings account. So your initial deposit is $100 that pays 4% per year, compounded monthly, right? So you get 4% per year, but it's compounded monthly, so you get essentially 1% a month of compound interest. And on the first of each month, when that compounds, you're adding $50 more into the account. So you're adding money into the account and you're earning interest at the same time. So you're really trying to grow this account. So the first thing we want to do is we want to set up a recursive sequence. So A sub naught in this case is just the initial amount that we started off with, which is $100. Right? That's our A sub naught. Right? And then A sub n is going to be equal to 1 plus our interest rate, which is 0.04 in decimal format, divided by, well, it's compounded monthly, so that's 12 times a year, right? So I'm sorry, it's compounded monthly. I believe I said it was, you were going to get 1% every compounding period, but it's actually going to be 1/12 of 4% every compounding period. And so that's multiplied by and usually, well, whatever. And that, we usually use, I'm going to go back here and just change this all to big A. We usually use a capital A to talk about the amount that we currently have in an annuity, just so we don't get this confused with another sequence. So you take that and multiply it by the amount that you had from the previous compounding period, and you add in the new amount that you are depositing, which is you're putting in $50 each compounding period here. And that's the amount you'd have after a certain number of iterations, right? So the second part says to use the table feature to list the amounts of the annuity for the first 6 months. So what we can do is we can go ahead and plug this whole this in to our sequence program. Let's go ahead and do that. So what we have to do here is we're going to use our calculator. We're going to, in our calculator for this part B, we want to use the table feature, so we have to enter it into our calculator. We're going to put U sub n, this is what it's going to look like in our calculator, is going to be equal to 1 plus 0.04 divided by 12, that's pretty much the same, times, and because this is a recursive formula that you're entering into your calculator, it's a little different. You're going to do second function, right, and hit 7, second 7, and that will give you a little u, and then you're just going to do open parentheses, n minus 1. This is going to give you the n minus 1th term of your sequence, and so it's a recursive way of defining this. And so you're going to multiply, you're going to do your compound interest on the amount that you had from the previous iteration, and then you'll just go ahead and add 50 to that. So that's what you're going to plug into your calculator. That's what it's going to look like in your calculator, and then you should be able to get a table of values, right, for amount each month. The table will show you the amount that you have after each month. Right. And the question is, after the deposit, so we can answer part C using the information in that table. So the question is, after the deposit on March 1st is made, is there enough in the account to pay for the Cancun trip? So you start off with $100 on September 1st, right? At the end of September 1st, which would be on October 1st, right? You're going to have, looks like, $150 after you deposit. You get your interest and you deposit another 50, right? And so A sub naught in your table is going to be your initial amount. A sub 1 is the amount on October 1st. A sub 2 is the amount on November 1st. A sub 3 is the amount on December 1st, and so forth. And so December 1st, January 1st, February 1st, and at March 1st, you're going to have $404.53. So is that your table here, A sub 4 is 404.53. So you're not going to have enough because you need $450 for spring break, and you're only going to have $404.53 in your account at that point. Sorry, that should be, I take that back. March 1st should be A sub 6, right? That's 6 months after your first deposit. You should be to March 1st. right? So you don't have quite enough money, right? So the question is, if you deposit $60 a month, will that fix it? So in our calculator, you know, we're going to plug in into, we're going to go to y equals, and we're going to plug in u sub n is equal to, same thing except we're just going to change the periodic deposit amount. So it's going to be 0.04 over 12 times, once again, you have to write u to the n minus 1, but then just do plus 60, or just all you have to do is change it to plus 60 from plus 50. All right, and then once again, go back to your table. And then if you look at your table, you'll see that in your table a sub 6, when n is 6, is going to be 465.03. So you would have enough if you deposited $60 a month at that interest rate. So if you're saving for spring break, right, you would have to deposit $60 a month so that on March 1st you have the money that you need. Okay? So, that is an annuity. And by the way, these are all ordinary annuities that we just talked about. This only works for ordinary annuities, and ordinary annuities are annuities where you deposit your periodic payment at the same time that interest is at the same time that interest is compounded. Payment and interest at same time. At same time. So that's what an ordinary annuity is. And that's the only type we're going to talk about here. Now, so an annuity is an investment where you're actually making money, right? The other type of securitization, which is just you paying off a loan, essentially, or paying off some sort of debt, whether that's a loan, whether it's credit card debt, right? So an amortization, right, is a plan to pay off a debt with regular payments So with regular, let me just back up here for a second. So with the amortization, you're making regular monthly payments. Right? So it's a plan to pay off debt with regular monthly payments while the debt continues to accrue interest. So the debt, you're sort of trying to pay it off faster than the interest is going up, essentially, or the interest is increasing the debt. Right? So it's a very similar formula. You start off with whatever the amount that you borrowed. That's your A sub naught is just your initial amount that you took out, that you borrowed in a loan, or that you have as debt in a credit card account, or whatever the case may be. Right? And the amount that's left over, that's still left to be paid off after a certain number of months, is going to be 1 plus your interest rate. How much are they stacking on each month that you know, to what's left over of your account? Because, you know, no debt is free debt, right? You always pay for debt, right? You're not just paying off the debt, you're paying them for letting you continue to have the debt, right? So they're putting an interest on each month to what is left over. And because this is always monthly, instead of just having, you know, the bottom being n, it's just always 12. It's always 12 times a year, just when you're doing an amortization usually. Times A to the amount, so the amount that you had after your last payment, right, we add that amount of interest to that amount, right, and then you're going to make your new payment, which is going to decrease because you're going down because you're trying to pay down a debt as opposed to accruing interest on an annuity, right? In this case, you're going in the opposite direction. You're trying to get rid of it. So you're paying down this debt, and so essentially each month, right, the amount that you had left over gets compounded at that whatever interest rate. Obviously, so is a lower or higher interest rate better? You'd rather have a lower interest rate you want a high interest rate in annuity, right? Because you want to make a lot of money, you want to compound quickly, but you would rather have a really low interest rate on a loan or credit card debt, because the higher the interest rate, the more they're going to keep tacking on each month, even as you pay it off, which means it's going to take you longer to pay it off and it's going to cost you more money. So we'd rather have this R be as small as possible for an amortization. And so they take the amount that you had the previous month, multiply it by, compound it by whatever the interest rate is each month, right? And so because it is, you know, R is still an annual percentage rate, you have to take that and divide it by 12, because they're not adding on, like let's say you have a 7% interest rate on your credit card, which would be actually a pretty good interest rate. It's more likely it's a loan that has a 7% interest rate. In any case, they're not going to add on 7% of your total debt per month. They're going to do 1/12 of 7% per month. So it's going to essentially work out to a little more than 12% over the course of the year. But you're not going to get killed with interest. Well, I mean, you still might get, I guess, but not quite that bad. And then after they've added on that interest, then you take away for your payments. So you don't get to like do the payment first and then do the interest on what's left over. They do the interest and then the payment gets taken off afterwards, right? And so that's how amortizations work. And once again, the recursive part of this formula is valid for n greater than or equal to 1. For n equals 0, we have our b, the amount we started with. All right, so I'm going to give you a word problem to work on with an amortization. I want you to tell me with your calculator how long it's going to take these people to pay off whatever debt they have. All right, so with this next one, John and Wanda borrowed $180,000, which, you know, to buy a house. Their interest rate on that loan is 7% per year. It's compounded monthly, as most are. And that's over 30 years. Their monthly payment is determined to be $1,197.54. So that's how much they're putting in per month. So find a recursive formula that represents their balance after each payment. Determine their balance after the first payment is made. Right? And the question is, when will their balance drop below $170,000? Right? And the people in the loan office have already actually done a lot of the work for us, because what they're saying when they're saying 30 years here is that they've calculated that this has to be their payment for the loan to be paid off in 30 years. So if they pay exactly this amount per month, after 30 years, they will have paid off the whole mortgage. And usually mortgages are monthly payments are calculated for like a 30-year mortgage, where you'll have the house paid off after 30 years. So that they've already calculated how much they need to pay per month to have exactly paid off after 30 years. So you just want to go ahead and answer these other questions, which is find the formula, determine the balance after the first payment, and when is the balance below $170,000. And then once you go ahead and just make sure that when you get to n is equal to 30, the balance is 0, as it should be, right? All right, so give that a shot. All right, so first thing we'll do is we'll go into y equals in our calculator, and we'll plug in u sub n is going to equal 1 plus 0.07 over 12, right? That's our interest compounded per month, times the amount left on the amortization. So what it's going to look like in our calculator is times it's going to be times u sub n minus 1, right? Minus the amount you pay per month, which is $11,097.54, right? And so that's what you're going to plug into your y equals in your calculator, and your u sub naught, of course, should be, you need to make sure you plug in your u sub naught, u sub n min. Below u sub n, you should have your u sub n min, the amount that you start with, needs to be 180,000, right? For this to work. So that's what you're going to plug into your y equals, and then you'll go ahead and hit table. So for part B, you'll hit table, now that we have that recursive formula. And determine their balance after the first payment is made. So that will be a sub 1, which in your table A sub 1, you look at our table, it's going to be $179,852. Right, and if you look at the table further, you can see the balance will be below 170,000. You got to scroll down for a long time.
Take a while to get to that. It is 59.
Yep, because we know it's going to be a while, so we're just going to keep scrolling down. Remember, each n is only a month, right? So we got to just scroll down. And so it's going to be a ways, right? Because it's probably going to be a few years that it's going to take to pay this off, right, to get it down to that point. We know it's going to take 30 years to pay off the entire thing, right? And so it looks like it's going to take us until the 58th month. So after 58 months, we're going to be down to $169,000 left to pay off. $169,852 after 58 months. So that's almost 5 years. It's going to take us, 58 months is a little bit less than 5 years, right? 60 months would be 5 years. So it's going to take us a little bit less than 5 years to get down to $169,000. Now the reason, what ends up happening here is this payoff, you know, because you're taking stuff off at a pretty rapid rate, it gets faster and faster. At first, the interest, because you're doing 7%, such a large amount of money, right? The interest is sort of offsetting the amount that you're paying off, and you're paying off only a little bit of the loan each time. But as you go on, because your payment stays the same and the interest becomes less because it's on a smaller amount of money, the payments, more of what you're paying is actually getting rid of the current balance and not being offset by the interest. And so this rate of payoff is actually going to accelerate. And so even though after 5 years we've only lost $10,000, if that went at a linear rate, right, we would never pay it off in 30 years, but that's going to accelerate because we're paying off a smaller and smaller amount. So the interest is going to be smaller. It's going to offset that $1,100 or that $1,200 that we pay each month less and less. And more of that $1,200 each month is going to get rid of the current amount that's there. And so that speed is going to increase over time. So that's how we deal with that. And that's actually, I mean, that's pretty much how loan payments work usually. Some of them are a little bit more complex than that, but the same general idea is what we're following. Okay? All right, guys, let's start looking now. We're moving on to section 12.2, and we're going to check out arithmetic sequences. Right, arithmetic sequences are a specific type of sequence. We've actually seen some of these already. We're just going to sort of define what they are now. So an arithmetic sequence is a sequence where the difference between any two successive terms is constant. Or between any two consecutive terms, I should probably say. The difference between any two consecutive terms is constant. Right, an example would be like 3, 6, 9, 12, and so on, right? The difference between 9 and 12 is 3. The difference between 3 and 6 is 3. Right? That's an arithmetic sequence because we're just adding the same amount each time to the previous term to get the new term, right? And so it's really and so as a result, because we're just adding the same amount to the previous term, right? This is a really easy thing to define recursively, right? So we start off with some value a sub naught, right, equals some value. And then a sub n is just equal to a sub n minus 1 plus that, whatever that difference is between them. And so this is called the common difference. Right? We start with some value which we'll just call, a, So our initial value, a sub naught, we're just going to call that a. And then every subsequent term is just take the previous term and add the common difference to it, and that gives you the new term. And so, like I said, it's very easy to define recursively. So okay, so what do we think? Is it arithmetic? Yep, it is. Right? What is D? What is our common difference? 5. So a sub naught is equal to what? And a sub n is going to be equal to what?
So n minus 1
Plus
5.
5. It's going up by 5 each time. Right? And the same would be true if it was going down. Let's say if it was like 7 to -3, then the common difference would just be -5, right? So arithmetic sequences can increase and they can also decrease. So that's important to take note of. Now, in some cases, you're just given, the terms, first, second, third, fourth term of a sequence, right? And you're asked to write a recursive formula for it, identify that it is arithmetic. It's important to know, be able to see that it is. But other times, we know that there's other ways of defining sequences. We can define them recursively. We can also define them explicitly, which was the first way we define sequences. So for instance, All right, so first of all, is it arithmetic, right? So the nth term of the sequence is 4 minus n. The n minus 1th term of the sequence is 4 minus n minus 1, which is just going to be 5 minus n, right? And so if I do s sub n minus s sub n minus 1, I will get 4 minus n minus 5 minus n, and I will end up with negative 1. So there's your constant difference between any two subsequent terms in the sequence. So it is arithmetic, right? Find the recursive definition, right? D is our D is negative 1, right? And t sub naught is going to be equal to 4, right? And D is equal to negative 1. So that means t sub n, right? Or I guess if we're defining this recursively, well, yeah, the recursive definition is that t sub naught is equal to 4, and t sub n is going to be equal to t sub n minus 1, right? We're going down by 1 each time. Okay? All right, so now we can find a recursive formula for, so this is once again, this is the recursive formula, and this is the explicit formula. And so we can find the recursive formula for the sequence if we have the explicit formula, but what if we want to go in reverse? What if we have certain information about the sequence and we want to find instead of the recursive formula, we want to go ahead and find the explicit formula. So the 8th term is equal to, a sub 8 is equal to 75, and the 20th term is equal to 39. Right, so the 8th term is 75 and the 20th term is 39. And we want to go ahead and figure out, first of all, what is the common difference between the two? And also, what is a sub 1? What is the first term in the sequence? So the first thing we should do is realize that, well, a sub 8 by our formula we had is just equal to a sub 1 plus 7d, right? And minus 1 times d. And a sub 20 is just equal to a sub 1 plus 19d. And we know that a sub 1 plus 7d equals 75. And a sub 1 plus 19d is equal to 39. So it appears here that we have a system of equations, right? So what I would do with the system of equations, I would subtract the bottom equation from the top equation, and I'll get negative 12d is equal to, it's going to be 26, right? Is that right? Is equal to, yeah, negative 12, sorry, 36. Yeah, I don't know where I came up with 26. Is equal to 36. And so d is equal to negative 3. So the common difference between each term is negative 3. And that means a sub 1, if we plug d equals negative 3 back into either of the original equations, if we plug it back in here, we get negative 21. We add 21 to 75, and we'll get 96. So a sub 1 is 96, and d is equal to negative 3. Right, so that makes it really easy to write a recursive formula. Right, a sub 1 equals, or usually we use s when with recursive formulas. So s sub 1 is equal to 96, and s sub n is just equal to s sub n minus 1 minus 3, right? Subtract 3 from each subsequent term to get the new term. And then the nth term formula, the explicit formula, a sub n is going to be equal to a sub 1, which is 96, plus n minus 1 times d, which is negative 3. Right? And so that just ends up becoming minus 3n, we had to add 3. So 99 minus 3n, if we simplify that. That's the nth term formula, that's the explicit formula. That's the recursive formula, right? And we can use this system of equations right here. If we know any two terms, and we know which term they are, in addition to knowing what the terms are, that they're 75 and 39, we know that they are the 8th and 20th terms respectively. If we know any two terms of an arithmetic sequence, that's all we need to know. It's just like with a line, any 2 points define a line. Any two terms in an arithmetic sequence fully define the arithmetic sequence, and we can just use that system of equations along with the nth term formulas to find out d and a sub 1. So arithmetic sequences, not so bad. All right, so we're going to stop there. We'll talk about finding the sums, the partial sums of arithmetic sequences tomorrow, along with getting into geometric sequences. Your homework for tonight. So your homework for tonight is from the following. The first one is from the handout from yesterday, from the old handout that I gave you yesterday. And this is from the new handout that I will email out to everyone today. All right, have a great day. Remember, this is the third to last class. Friday is the last class, and I'll let you know when we're going to do the final by the end of the week. Have a good one.